All right, everybody. Let's start. Okay, who knows what movie this is from? What's going on here? What makes it a Mexican standoff? Not that it has anything to do with Mexico, but well, what's a normal standoff? Describe a normal standoff in the Wild West, the Old West. Yeah. Yeah. Like
And there's always a tumbleweed.
And there's always a tumbleweed. So it's like Hamilton with the tumbleweed, right? I count more than two. So what do you do in this situation? Who do you shoot first? Who do you keep your eyes on? If you remember this movie, this is at the end of a very long movie. It's a great movie, 3 hours long or so, but it's a masterpiece of this genre, which they call spaghetti westerns. Anyone know why they call them spaghetti westerns? What's that? Yes, Sergio Leone specifically, and Ennio Morricone did the soundtrack, and Ugo Montenegro, I guess, performed it. But a lot of Italian actors, and they would just speak their parts in Italian, they dub them in English later, and it's all filmed in Spain. So none of it's actually in the Southwest US, but it kind of looks like it a little bit. But this scene shows an interesting situation. Here's a little further away. It's in the middle of a graveyard, and these guys are shooting it out over something written on a stone. And I don't want to ruin it for you, but just considering this, you have three characters. Tuco, the guy with no name, who Tuco calls a Blondie, so he's marked with a B. And you got Angel Eyes, who is the bad guy. So the good is Blondie, supposedly. The bad is AE, and the ugly. Now, B and T, they draw from the same side where they have the whole strip, whereas Angel Eyes draws the other way. And they position Angel Eyes different points, chooses a different place to stand. Say at one point he's very close to, another point he's very far away. Think about all of the implications of your choice of who do you shoot first. Once one guy shoots, what do the other two guys do immediately? They shoot someone. If you were, let's say you were Tuco, and Blondie shoots, whether he shoots you or not, you got to shoot. Who do you shoot? You shoot the other guy? What if Blondie was shooting him? You're still alive, but should you also shoot the same guy? Or should you shoot Blondie? Because he's taking care of that other problem, now you're taking care of him.
Depends how addicted you are. Because it's all about, it's a decision. Do you value your own life more, or do you value having everyone else losing more? So if you value your own life more, you always shoot the other person. Or sorry, if you value everyone losing, you shoot the other person. Because then if they are shooting you, then you shoot the person who's not getting shot at. So then all of you die. If you shoot the original person and the other person shoots the original person, then you both live and the last person dies. And then it's the other way around. Then like, you all die again. So.
Yeah, they all do not like each other. They all want the other two guys to die, and one of them will get the treasure. Yeah, so where the point of the gun is a big part of it, because you can only get a shot off if you get off quickly. And knowing that Angel Eyes is doing cross draw means that it's going to probably shoot Tuco first. And if you're Blondie, you know that. Maybe you draw, knowing he's gonna take care of Tuco, so you take care of Angel Eyes a little bit after he takes care of Tuco, maybe. But there's a lot of elements to this, and it's really hard to keep track of it all, isn't it? Well, there is a science behind keeping track of all of the elements in a game. What is that science called? Anyone? Game theory. Very good. And we will be discussing that today. First, let's talk about some items from homework and other things. Block representations. We're going to talk about a couple examples of how to present blocks. Now, for last week's homework, the regression and then the binary classification, some of you, I really like this. You presented the mean squared error in both the test set and the training set. Now, one of the things you can see as you train your models in machine learning is there will often be a difference between those two. What does it mean when there's very little difference? What do you guys think? If the mean squared error is almost the same for your test set and your training set, what does that mean? The distribution of those things. Yeah, the distribution between the two are the same. But it also means that your model works. It generalizes on unseen data. And that's what you really want. What does it mean if the error is way higher on the test set than the training set? It doesn't. Now, there are models that can eventually learn a training set so well, they will fit it too well. What is the word you have for that? Overfitting. One of the ways you can make sure you're not overfitting or guard against it is watch that difference. The difference in the error when you're using the training or the test set. And in machine learning, oftentimes we call that the loss. So if your loss is going down, it's better and better, yay, and it's great. But when you compute the loss with respect to the test set, really bad, then you know you're overfit. And sometimes it's good to take a step back at that point. Some people actually train their models until they start overfitting and they just stop there. Now, this brings up a third set. Some people will have a training set, a validation set, and a test set. This is because if you do too much stopping based on your test set, and you keep doing this, eventually your test set is affecting your model, and it's no longer a pure holdout test set, is it? So if you do things in the middle of the training, where you're choosing to do one thing or another based on that difference between the loss of the training versus test, you actually should do it with the validation set. So you have, in a sense, you have two test sets. One that you're going to use to guide the training, not train, but guide it. And then one that you never use except at the end, test it. Okay. Now for linear regression, what most of you did, and was great, was you found a numerical input variable and a numerical output variable. So the independent and the dependent. And you found ones that were vaguely related, that there would be some kind of intuitive line that would form from it, whether it goes this way or whether it goes some other way, doesn't matter. That was good. There were a couple of you that did not do that. A couple of you that for the linear regression, you chose like something that went to a class, you know, from a numerical to a class. And that didn't quite fit the homework, but I just wanted to be clear about that. Linear regression is typically done for numerical input and output. And it's going to be important later when we have many dimensions coming in. And there will be some number coming out. There'll be a linear model, a high dimensional linear regression. And we're going to do things that will be generalizations of things. So if you have a bunch of data organized like this, you know, maybe there is no line that fits it, but maybe there's some higher order function that fits it. And we will find ways to take weirdly shaped manifolds. This is a manifold, weirdly shaped manifolds, and contort them back into linearity. And then do a linear model on the contorted space. So this is just a beginning, a foray into more complicated discussions. Okay, some of you, I can't remember, you know, how many, whatever, they were doing great. You had some linear regression data, you did that part, and then set your threshold maybe here, so that everything was one class. That wasn't quite what I was looking for. What I was looking for was to take this linear regression that you just done, set some threshold somewhere relatively in the middle. There needs to be some things on both sides of it. And that turns or converts this linear regression problem into a binary class problem. So you still have a numerical input on the x, but then on the y becomes a 1 or a 0. And this kind of thing occurs in the real world all the time. You'll have a FICO score, right? Credit score, and that's a linear number. But whether or not you get a house loan or not is a 1 or a 0. So this kind of thing comes up in the world. Okay, some of you just didn't do the discretized analysis, the binary class. Some of you just forgot that. Okay, one of you in the homework addressed me as doctor. I'm not a doctor, I'm a professor because Gonzaga calls me that, but I never got a PhD. I got a master's, not a PhD, so I'm not a doctor. Okay, one of you made the comment in homework, it does not make sense to compute accuracy from a linear regression. And most of the time that's true. But when we set a threshold and we convert everything to be 1s or 0s, then it does make sense. Now, obviously, we're taking an example that's not made for binary classification, we're forcing it into that. And I'm doing that with you guys because I want to start out with something very simple before we go off into these higher dimensional complex things. It's really just a method for conveying these ideas. Okay, a few of you stored the data inside the model object. That's not where I want you to store it. I want the model to be something that it's only going to store things like its own parameters, the things that it needs to know to make predictions on data. The data itself is completely separate. And the data can be a data frame, it can be a data object you make up yourself, it can be a CSV, it can be all kinds of things, but that data is something you
what everyone does. I think it's a good way to think about it. Okay, some of you did a really great job of explaining yourself in the notebook with comments like, here in this step, we're going to do this, and here we're going to do this. Now, I didn't take off points if you didn't do that, but if you do that, I really appreciate it. And it may add in points later. So please do that whenever you can. Some of you were missing the RMSE or mean squared error. Any questions? No? Okay. Now, R2 or R squared is a measure of the variance. How much of the variance does your model explain? Now, in the world of statistics, if you're just doing linear regression in statistics, R2 is the go-to. That's the go-to. That's what people use. That's how they talk. But that's not exactly how machine learning people might think. So we're taking this as an example of much more complex things we'll be doing. And if we had an example where we had this, weird curvy manifold that we used a kernel function, they're called, to contort it back into some kind of linear situation, then it doesn't really look like this. We're just forcing it to look like this. R2 is not the way we think of it. We really like to think about the error. How far off are we on average? And that's going to relate directly to how many wrong answers we're going to get or how bad our predictions are going to be. It's more a way a machine learning person thinks. So these two gray rectangles, what are they? Yes. What's the difference between them? Yeah, it's exactly the same game state, right? These are two totally fine ways to represent your blocks. I saw in my office hours a minute ago, someone showed me they were doing it like this, but flipped upside down. That's fine too. Some people have been trying some things. They let it run for 10 hours and it did not solve. Who else had that experience? All right. So one of those people said with 8 blocks and 8 positions, it worked fine. That you get it there. But with 9, it didn't. So this may be one of those cases where going to the 9th block means that combinatorially it's going to be too many steps for your computational power. That may be true. If that's true, you'll find that, you'll talk about that in the homework. What I want to get down is the ability to operate in blocks world in, have the objects all ready so that next week, when we use an actual strategy to solve this problem, you'll have most of the pieces in place already. Okay, one thing we can do is you can avoid states that were already seen. So one person said they coded it up and it was going along and then it would get stuck. You'd have, this block 6, maybe it go here, and then it go back to here, and then it go here, and then go back to here. So there's no need to explore a state you've already explored, typically. Now, by avoiding states that you've already seen, it's possible that your game might get stuck in some other new dead end. We'll find that out. You guys will explore, you'll report back. Keep track of previous states. Very good question. You need a state hash key. So hashes in Python are very efficient. A hashing function in general, takes some key and maps it instantly to a value. And that value just, some, it could be anything. In Python, it can be any object, but here we're going to be mapping it to a Boolean. And that Boolean actually be stored somewhere in memory. But this key can only be either a string or an integer. So we need to be able to represent this state, the game state, as a string or an integer. I think the string is easier because you can just take whatever object that is, however you represent it internally. It's a list of lists, or maybe it's a two-dimensional numpy array. Whatever it is, you can just put str in front of it, print that out to a string. Now you have your hash key. And you can have some, you can either have a dict called scene, and scene can have the keys can be those game state hash keys, and the values could be a Boolean, but even more simple is a set. So in Python, a set is implemented almost exactly like a dict, but the value is either a 1 or a Boolean true for being present, or it's just not there. So a set is probably the way to go. And one way to declare a set is to take an empty list and wrap it as a set and say, scene equals set that. Then let's say you have some game state. You get the key that represents that game state, the hash key, whether it's the string of your two-dimensional array or whatever. And then scene dot add key. And then you can later on, if you're about to try that game state again, you can say if key in scene, then skip whatever. Don't do that state again. That's the kind of thing you could do. Another thing which might free things up is when you're moving a block, right? Let's say you're moving a 3. Instead of just moving it to the left or the right, let's say you can move it to any state. Now, one of you, instead of creating an initial random state and doing valid moves between them, just did an initial random state again and again and again forever. I would not recommend that either. And if you did that, you also are in effect retrying many states, because you will randomly come across the same states again and again too. Any questions? All right. My great uncle went to high school with the guy on the left. Any idea who that is? John Nash. Does that sound familiar? Who is he?
He's that guy that made that fashion video.
Yes. Now, who's got it right? Russell Crowe. In what movie? Beautiful Mind. Who is he playing? Yes, he was playing John Nash. A Beautiful Mind is about John Nash. Now he has trouble. He's actually schizophrenic. He sees people that aren't there, has conversations and holds friendships with people who aren't there. Some people think that the difficulties in his mind also helped him achieve things in mathematics that no one else could have done. I don't know, but my uncle told me that my great uncle told me he was difficult in high school too. was a challenging person. But what he came up with was brilliant. And it was a way of approaching games that no one else had tried before. But games applied more broadly. Now, we're going to do an example. Who has heard of the prisoner's dilemma? Keep your hands high. I want to choose two people who have not heard of it. How about you two? Never heard of it. You have heard of it? Okay, raise your hands if you have heard of it. I'm going to choose two people who have not. How about you? And Claire. Okay. So stand up here. One person here, one person here. Okay. Pretend you guys were, you don't have to get that far. You guys were caught in a crime, okay? And the police have just enough evidence to believe they can probably get you both on something, but they really want you to squelch on the other one. Okay, you look up here. Let's say that you're A and you're B. This is a payoff matrix. So for every option of what the other player does, you can see what the payoff would be to each player. So if A stays silent and you stay silent, I have enough, the police have enough to put you both in jail for a year, 1 year. Now, the police like to offer a deal, right? They usually put you in separate rooms and they offer you a deal. And they'll say to you, hey, if you give up B, then you get nothing. You get to walk out today, scot-free. Of course, B's gonna get 3 years of jail. B, we're gonna give you the same deal. If you talk, but you have to talk first, you get to go free today. But A is gonna get 3 years of jail. See that? Now, what happens if they both talk? They both get 2 years. That's not great. What is going through your mind? What are the options? Like, why would you talk or not talk to the police? All right. Let's say that you think A is not going to talk. What do you do?
I'm looking at my best interest. I'm sure. I'm looking for, I care about the other person. I would probably also stay silent.
All right. If you're two criminals who just met up last week to do this crime, what do you think you'll do? You'll both betray. That's typical for average criminals. That's why police separate them into separate rooms. And here we see the mathematics of it. Now, if you guys totally trusted each other, you would both stay silent and you would do a year in jail each. For B, there's pressure going to go this way, isn't there? And then for A, there's pressure to go this way. This, of course, pushes it down to here or here, and the only way to resolve that is you end up in here. This is what's called the Nash equilibrium. This square down here is the only place that has no pressure to go anywhere else from anybody pursuing their own selfish gain. So the Nash equilibrium is the location on the payoff matrix where there's no need, no desire for an individual to be pushed to an adjacent, has to be adjacent to an adjacent square. Intuitively, it makes sense, right? Now, let's pretend you guys didn't trust each other at all, and you were still selfish, what else might keep you silent?
The other person has dirt on other things.
Ooh, yeah, so he's bringing up the idea that maybe something external to the game as is defined so far, right? What else other than dirt?
If it matters how much total time is served, like between both parties, the least time served.
Yeah, but that still assumes you care about the other person.
Well, and if it matters. to someone else.
Okay, that's a good way to think about it. When mafiosos don't squelch on each other, why don't they? Snitches get stitches. Yeah. Why do snitches get stitches?
I mean, even if they don't, like, get ripped up, but I know.
Are the stitches represented on this payoff matrix anywhere? No, they're not. Okay, you can sit down. Thank you. Okay, who knows what movie this is from? Same movie. How about now? Which one? This is in part 2. So this guy who works in the Corleone family is going to testify against them. He's already signed an affidavit with the FBI. He's actually been living in a safe house with the FBI, and he's all ready to testify in Congress or in a congressional committee. But then Michael Corleone shows up with this guy. Has a very unique bolo tie, doesn't he? Where do you think he's from? Sicily. Turns out it's the brother of the other guy. So Michael comes to court and he brings that guy's brother and reminds him of a whole lot of things. And in the end, the guy doesn't testify against him. He changes his whole story. He says, "Oh, I know these guys through the olive oil business. I don't know what you're talking about. I think there's just some confusion here." And of course, the FBI lawyer, whatever, to the right of him, just is very surprised, flummoxed. But he did not talk because he was reminded of something. He was thinking it was one kind of game, but now it's a different kind of game. And the term we use is finite or infinite. And the infinite game would lead to this silence. And the word they would use for silence is omerta. But that, not snitching on the other people in the game, it comes out because that payoff matrix doesn't show the whole picture. There are other steps after it, and another step after that. So, is war a finite game or an infinite game?
Depends on what you define as. If you're talking about a single instance of it, then yes. If you're talking about like the competition between countries, then no.
Why is the competition between countries? Were you saying that's infinite?
It's infinite until one country falls apart because you can define a war as like a financial war or anything like that. Like you can define either competition or like conflict between countries as war.
Mhm.
And if you define it as conflict between countries, then there's a lot of conflict constantly going on between countries. If you're defining it as an instance of like direct military conflict, then that is an instance that can end. But it may not be just that. It depends on your definition of what war is.
How about business? What do you guys think? Infinite or finite?
Infinite.
Who thinks business is an infinite game? Who thinks it's a finite game? So why is it a finite game? If it comes to an end, did you win? So it only comes to an end if you lose, right? Are there people who think of business as a finite game? What makes you think that? So people, some businesses are too focused on short-term transactions.
There's also fear of rules and how like to the finite amount of money in the world, the finite number of people. So after a point, stop growing.
So yeah, there could be a point where you can't win anymore. Is poker finite or infinite? Okay. Who said that? Okay. And if you think of not just the game, but your whole poker career, does that change things? Is that going to change the decisions you make?
Yes.
How?
Well, if you're over the long term, you're trying to be more cautious. Play risk early on, and cautious later on. I know it's stock investing, but just one game, certain things are better in the short term.
So if you yourself see yourself as playing a finite versus infinite game, it changes your actual choices. Yeah. How about, and this is related to poker, lying. Going around lying to people. Is that finite or infinite?
It makes you have to put the line first.
How does that apply to poker? Go ahead.
I was gonna add on to the line, but also you're famous enough to get that written down in history, like something Greece or something. You can just hard to get that. That's that is history.
Yeah. Yeah, if you are able to get maybe some level of fame or keep moving around and lying to different people each time, maybe you can keep going. But if you're, let's say you're a poker player and every single hand you bluff, that may work in one game, but it's probably not going to work in game 2 or game 3, or especially if you're a professional poker player, people come up against you and they know you bluff literally every hand. What happens when a finite player plays against an infinite player in the same game? Can you think of any examples? There's this one guy online named Simon Sinek who talks about this a lot, finite versus infinite games. And he said at one point that he felt that Microsoft was playing the finite game and Google was playing the infinite game. So Android phones are still around. That's a Google thing. Are Windows phones still around? There was a time when the best Windows phone was better than the best Android. When you look at that business situation, what kind of things would you look to see whether Microsoft was in fact playing a finite game? And what would that even mean for business? Businesses want to live forever, right? So what would it mean for business to play a finite game?
To release a product without limitations.
Maybe, yeah.
People like, we have to hit this certain like market cap, like
Yes.
goal, like 5 years. So we're gonna make these decisions to get that. And
Or
not really
even
get
shorter
better.
term, like look at this quarter, right? Is there an incentive for a company to play that finite game and do well this quarter at the expense of the future?
Person in part, like the CEO or something, is like probably gonna die, so he just wants to make as much money as possible before he dies.
It's not usually death, but it's usually things like their contract. A lot of these contracts are written such that if you hit this stock price within this many quarters, then you get this much of a bonus. Then there's a general employee of the company who knows that, you know, if the stock price hits this much, then I could sell that much and probably buy a house. So in many layers, the market incentivizes you to play the short-term game and make the windows small, which now no one uses. Something to keep in mind. Another situation with much more dire circumstances is this. What is this from? Not Iran, not Saudi Arabia. But is that what you're going to say in the back? Afghanistan. So these Afghanis definitely wanted to live in the US. They definitely were pro whatever it is we are trying to put out there in the world. They did not want to stay, and a lot of them died hanging on the sides of these planes. It's one of the most tragic things I've seen in my lifetime. Years ago, one thing we said after we went in was, and how did it all work out? Well, not bad. The Taliban are gone. Al Qaeda are on the run. It was going to be rather, I would say, effective use of Afghan forces. Well, that statement didn't age too well. The Al Qaeda did not really run away, and the Taliban were not gone. Our commitment would not be an open-ended, that we begin to draw down our forces this July. That was said in 2011. We said things like that all through the war. We're going to leave, we're going to leave, we're going to win, fix it, and then we'll leave, and it'll stay fixed. A perpetual sense of imminent departure reduced the ability of U.S. officials to plan for the long term. It's written after the U.S. left Afghanistan. At every point in that conflict, the U.S. was playing the finite game. Taliban was playing the infinite game. The U.S. had way more force, way more capability. We were organized. We had the support of many actors, and we still left, and it all crumbled apart. Same kind of thing happened in Vietnam, right? U.S. was playing the finite game. The other side was playing the infinite game. Okay, this is one of my favorite paintings, Winslow Homer, an American painter, The Fog Warning. It brings this dramatic feeling of man versus nature. Man versus nature is a great example of a certain kind of game. And with the games, there's so many different ways to describe games. We've looked at infinite versus finite. We've looked at a couple different other aspects that we talked about, but this brings up a new one. This is man versus nature, but this is also man versus nature. What's the difference between these two kinds of situations? Can't endure a storm, can you? Yeah. Does the storm want to hurt you? but he still could, right? Nature can kill you, just not give it in. What word do you think might describe this game, but would not describe this game? Keep going. Conflicts, that's good. Okay,
Say, with the book, you go on the offense.
that's right. There is no offense really with the fog. We call it non-adversarial or adversarial. This is a non-adversarial game. There's no adversary. Here, there is an adversary. There's an opponent. With the fog, how complex would your payoff matrix be? There is no B, right? There's just A. Player A decides to stay where they are. Okay, they get killed by the storm, they drown. Or they rowed ashore and now they live. Great. That's very simple. Just two cells. It's very simple. There's no complex interaction between players. But here, there is. Every move the boy makes is going to be met by some counter move by the beast. Every move the beast makes will be met by a counter move by the human. Adversarial games are inherently more complex. What do you think might be the most complex adversarial game that we are all part of right now? Life, or some people would say economics. That every one of us, we're trying to do well in life. And someone mentioned the finite set of dollars out there. We're all trying to earn some of those dollars. We're all competing with each other, but we're also cooperating with each other. And when a market goes up or down, that's a result of the reactions or the actions of hundreds of millions of people. That's a very complex payoff matrix. It's so complex that we just talk about it at large scale. Okay, is chess adversarial? Yes. Is Sudoku? No, it's more like man versus nature, but against storm, right? You're not playing against a wild beast, you're playing against a storm. How about Call of Duty? Yeah, that's adversarial. How about Duck Hunt? You guys even know what that is? Hey, yeah. It was old arcade game where you try to shoot ducks.
It scores mostly, so I don't know if it's considered adversarial, unless you're trying to get the highest score.
Well, the original Duck Hunt, those ducks weren't doing much to respond to your action. They either died from getting shot or not. Now, they did try to take evasive action, but it was all programmed in ahead of time. How about Minecraft? Depends on what?
What you're doing. I can play alone, it's not adversarial, but if you're playing other people,
Okay.
can't be.
Now, when you're playing with other people, they're usually your friends. You don't have a power to kill each other.
No, you can kill each other, yeah.
Kill each other?
Yeah.
You sword
Legal stuff.
or even the zombies, of course, kill you and survive. But yeah, I've never played Minecraft such a way that I'm trying to kill them because you should play with my daughter. So whether a game is adversarial or not is going to change how you act. Now, agency, or assuming the other part, your opponent, assuming they have agency or free will, is what makes it adversarial. And there's something called theory of mind. So theory of mind is the ability for a person to believe that another person has a different state of mind than their own. And this is not something you're born with. When they ask 3-year-olds things, this shows they do not have this yet. I'll give you a simple example. Let's say there's a boy and his older brother. His older brother puts a sandwich on the desk in his room, puts a box over it and says, "Don't touch my sandwich." As soon as the older brother leaves, the younger brother takes the sandwich from out under the box and hides it under the bed. When the older brother comes back, where will he look for the sandwich? We all know, under the box. But when you ask a 3-year-old that, they will say, oh, he's going to look under the bed because that's where the sandwich is. They don't yet have the ability to model the mental state of other people. That's something you learn. That's theory of mind. And it's very important. Now, why would it be important in chess to model someone else's state of mind?
Like candidates who like think they're gonna make a mistake.
Yep. In fact, there's been a lot of controversy in the chess world in the last couple of weeks. Who's heard of that? Okay, who's of an opinion? Well, first of all, who wants to tell us what the controversy is?
Well, there's this guy named like Hans Niemann. He beat like the best chess player in the world. Magnus Carlsen. Everyone thinks he cheated in overboard chess, but they have like a bunch of they like wand you and like make sure you can't communicate with someone else. So they should I say what like
Yeah.
They think he put like anal beads in his butt
That communicate with radio frequencies?
and I would tell him like what moves to make. Why not? I mean, I don't think he's good enough to beat Magnus Carlsen.
I don't think they did. I don't think he did that. That's my
Or was it
feeling.
the curtain rod thing too?
I haven't heard of the curtain rod.
Theories that, perhaps game leaked to, or someone on there leaked to him, so he was able to prepare beforehand using like a computer. So that's why like all the first two moves that he made, I mean, read it beforehand or prepped it, because he never played it before. And the guy did it too, like, just prepping it by random, so, I mean, I'm not.
Magnus played him again, like yesterday or 2 days ago.
Really?
Yeah, and he surrendered in like 2 days.
Who shredded?
Magnus.
Oh, that's the one. Yeah. I meant the one that he surrendered.
Oh, wow.
Well, he also on team and said that no, they when they compare those, they didn't actually beat Magnus, but at that point, he got very lucky.
That's the one.
Interesting. Anyway, I watched a few of Hans Niemann's games the last few days, and the guy is so incredibly quick. He's just amazing. He'll move his hands almost fast as I can see, and he wins. And I think he won fair and square. That's my feeling about it.
But it's like 2700 rated versus like 3300 rated.
No,
50 players. It's like,
Magnus Carlsen hasn't reached 29 yet.
no, he's like 30 something at one point. That's his max out.
Really?
I don't know if that's where it's at right now, but that's.
Anyway, I'm on Team Hans. Anyway, knowing the mental state of your opponent, for some people, they will judge them as being either a cheater or not. But it also helps you decide which things to play. But here's another variable for us to judge game types: perfect information. Chess is a game for which we have perfect information. Everybody knows where the pieces are. Can you think of a game where we don't have perfect information? Battleship, that's great. That was yours. Yeah, that's perfect. Another more mundane one would be poker, right? You don't know some of the cards on the table. When you see the first three that come up, not all at once, well, you, as the next two come out, you can see them with the other players, but you don't know what they have. Oh, we're talking about this. Yeah. So poker is a game where you have imperfect information. If it's just one game and you're never going to see that person again, you could treat it like a finite game. But when you go to competitions, you're oftentimes going up against people who have watched your past games. So it's best to treat everything as an infinite game, right? Okay, now we're going to learn a game called NIM. Who of you have heard of this game? All right, and this is getting you ready for a future homework assignment. So we have 4 heaps, we call them. First heap is 1, then 3, then 5, then 7. In each turn, you take from only one heap. You must take at least one, but you can take as many as you want, as long as it's from that one heap. So here's a sample game. Player 1 takes all 3 of those, and player 2 takes these 4. At this point, who do you think is going to win? Oh yeah, that's it. Good question.
The loser is the one who picks up the last piece. Remember, you have to pick up at least one piece, right? The loser picks up the last piece. So who do you think is going to win? Okay, so who for player 1? Who for player 2?
Player 1 goes there. Player 2. Okay, who now thinks player 1 is going to win? Who thinks player 2 is going to win? Is player 2 lost because they would have to take that last piece? Do you think this is a game that's mathematically mysterious, or do you think it's already been solved, so to speak? What do you think?
It's all in the format.
So if it's been solved, that means there is a known perfect strategy, right? So last year, I did this with a class about the same size, about 30 of you guys. Partway into the assignment, everyone realized this is a solved problem. The perfect solution is on Wikipedia for all you guys to read. And then we had a competition. They did not all do equally well. There were some people who won a lot and some who lost a lot. And we played hundreds of virtual games, so that statistically, if they all played the right algorithm, then they would have all won the same amount of times overall, but they did not. Why do you think that would be?
Just like human error.
Human error, yep. So this would be something you guys get to discover, because in a few weeks we're going to do this. Okay, now let's talk about a way of looking at these game states. This will apply to NIM. It will apply to chess, checkers, almost anything. But we got to simplify it to talk about it. We're going to simplify it into a binary tree. So this pretends, just for the sake of this example, that at every point you only have 2 choices. Okay? And let's say we're talking, maybe it's chess, who knows? But you've got white pieces and you've got black pieces. Now, Deep Blue was the first computer to beat a human grandmaster at chess, beat Gary Kasparov in 1997. The way he did it was by brute force looking forward into the future at all possible game states from the current position. So let's say we do that, and we have to have a way of deciding what's good versus bad. Well, for the black team, black pieces, let's say that these negative numbers are better. And for the white team, let's say that the positive numbers are better. This sets up something called the mini-max algorithm, where one side is trying to minimize The other side's trying to maximize. Let's say we played several states forward. We get a -1, 3, 5, 1, -6, 4, 0, 9. We need to be able to understand what would have gotten us there. If it was White's turn, White wants to maximize, which one of these do you think White's going to choose? I can't hear you guys. 3, and of course 5, -4, 9, right? Those are the choices that the white player made. Then, of course, the player with the black pieces chose a 3 there, knowing that would have been the lowest of these possible. So you're thinking ahead, what would the opponent play? And making your best decision, given the assumption that your opponent will play their best, right? And this gives us the output that we're gonna end up here. Because the player for White is gonna see that, okay, 3 is better than -4. The player for Black is gonna see that 3 is better than 5. And then 3 is better than -1. So if you know all the future states, and you can assume that your opponent is playing with a certain heuristic, just this number from -infinity to +infinity, then you can predict where the game will go. Now, is there a scenario where you don't have to look at all the options, where you can discover this path without looking at everything? Because remember, it's computationally expensive sometimes to look at every branch of possibility. How can we prune this tree?
Every tree that has, wait, branches, oh, what's the word?
Yes, if you know it won't be chosen, right? So let's say we've already looked at this branch going down here. We know the value of this is 3. We know that the player for Black is going to be minimizing, right? And the player for White is going to be maximizing. Now, if we get down to here and we look at this one, it's a 5. So given the choice, the player for White is going to choose something that's 5 or higher, for sure. That's all we know at this point. We don't know this is going to be negative or positive. We don't know anything about it, but we know the player for White is going to choose something that's going to be 5 or higher. That means this will never get chosen, right? If it's higher than this, it will never get chosen because at this point, it's not the player for White's turn, it's the player for Black. So if this is never going to be chosen just because this is higher than that, then we don't even need to look at this one. So we're skipping one search computation here. Obviously, that doesn't sound like much, but if instead of one, what if that turns into, another branching subtree with, a branching factor of 16 or 60 at each step? Then you save yourself, maybe 1,000 years of computation. This is called alpha beta pruning. It's a little bit hard to get at first, but does this make sense? Does anyone have any questions?
What's it called when you look further than one?
Your look ahead steps. You can look as many steps as you have computational power for. They're just called that look ahead. Playing forward all future game states.
So it starts out with it. Let's start with like first step. Or can you adjust that in case you're covering? So it's like stock measure. chess I had, it's rated like 3700 or something. Looks ahead like 23 moves. And we play really, really weird things just because it's like, oh, this line leads to me being ahead by 9 and 20 moves in the future. Like, is that pretty?
It's probably doing some pruning, yeah. Yeah.
Doing everything and then going back.
Because the branching factor, the number of branches coming off of every node, is the number of moves available to that player at that time. And chess will be different at different points of the game, depending on how many moves, how many pieces you have that are able to move. But it's usually more than the computational power of pre-program run by Stockfish. So they're definitely doing something. And they're probably using a number similar to this. In fact, they might be doing alpha beta pruning, where from Flash's perspective, you know, it's the number of white pieces minus the number of black pieces. So you want that number to be as negative as possible, or the alternative. And this number can be calculated just based on that. So at that game state, how many black pieces, how many white pieces, you get this number. And if you do this, you could do this 23 steps in the future, but if you get to something like this, you know it'll never be gone, you never go there, you can just ignore all the subtree down to other, 19 layers or 21 layers that are left. So that's probably what they do.
So like if you're deciding on that second branch that you're down, like let's just say that other one is -3, that like 4 steps in the future, it's like +16.
Yeah, see, it's a challenge because maybe this is a kind of a trick. Maybe this person, they know that, this one will have a higher number here, but they have an idea in their head that they're going to be able to, bring it back at some later point. So they would be willing to sacrifice some valuable pieces, and it's going to trick you to some position. So this number is a heuristic, and it's not perfect. It's far from perfect.
Does this algorithm start at like the peak of the tree or at the start of the tree?
The root is your game state right now. So whatever your game state is right now, you calculate, you play out a bunch of moves, and you start off with far in the future as you can go. So you start off, I'm going to go 23 steps into the future. You play all those positions out and calculate that heuristic. But then when you fill in your tree, you fill it in based on what that player would probably play in that state. And then backtrack a little more. Then you backtrack all the way back to where you are. Play ahead to the forward, to the future as far as you think you can go. Use your heuristic to come up with a value. Then you play it back. This, of course, assumes that you know what your opponent would do, which again is the theory of mind. Any last questions? All right, thank you, everybody.
Thank you, Professor.